So now let us go to the actual design implementation step. So I mentioned Verilog is what we are going to study today. Verilog is an extremely important language nowadays because 99% of today's designs are done using Verilog as a high-level language. There are other alternatives there like VHDL. It's also a very extremely good hardware description language. But in our discussion, we will be focusing mainly on Verilog, and you will be focusing on Verilog in our lab sessions also. So in a Verilog, there are many ways of writing code, and one way of writing code is called RTL, and this is what goes into your actual device. But there is other things like for test bench, you might be using Verilog, but not as an RTL. So in this picture, you're seeing a counter design, a counter RTL representation using Verilog as a language. Here you can see first you have module, a counter, and you have inputs, clock, reset, and you have the output CNT, which is 4-bit wide. 3 down to 0 is 4-bit wide. And there is an always statement you can see, which always at the rate positive edge clock and negative edge reset and all. We will come to this syntax in the next slide. But you have a counter designed using RTL representation, and you also have a comparator designed using RTL representation. And finally, what you do, these two modules are put into a high-level hierarchy called the chiptop.v. Here you are instantiating counter and comparator as U0 and U1, and you do the connections in between, clock reset and count, pulse, all those things. And finally, the pulse goes out of the design of the chip top as a output pulse. So your top level chip top has two inputs, clock and reset, and output is pulse. So what are you doing here? You designed counter, which is an RTL, comparator, which is also an RTL. You put a wrapper around it, which is chip top, which is your chip, the top level module for chip. And that's what you have. Your chip is ready now. So this is the chip design is in a design point of view. This is as simple as this. So let us go to the details of Verilog. I mean, little bit details of what these magic words are. So module is like the high level name for your design. So here module name is counter, and there are signal declarations which declares each signal and what is the nature of that signal. Some of the signals are input, some are output, and some are internal signals like registers. And after that, you are going to design a flip-flops. Basically, a counter is made up of flip-flops. Flip-flops, the basic nature is they have a clock, and many of them have resets. And this always block, you can see there is an always and there is a begin and end. In between there are some codes. So always at the rate postage clock and negative reset is a very common way of inferring a flip-flop or sequential elements. Here, counter is a sequential element. Counter has 4 flip-flops, and they are implemented as a postage clock, postage triggered flip-flop here. And let's analyze what it is. So at the always statement, you can see at the rate postage clock and negative of reset. What this mean? This list of postage clock and negative reset is called the sensitivity list. What it means is this always block is sensitive to these two input. This always block get triggered when postage of clock or negative of reset occurs. So the rest of the statements within that begin and end get activated only when this events happen. This sensitivity list event happens. So that is very important aspect in a Verilog based design. So in between the begin and end statement, inside that always statement, you see that all the code required for inferring the 4-bit counter. So here you can see that at the if there is a reset, so on the negative edge of reset, you enter into this block, and when the reset is low, you are assigning, you are initializing the value, initializing your counter flip-flops with the value 0. 4H0 means 4-bit 0. And else, if its counter is counter plus 1, which means if it is not reset, for every clock cycle, you are incrementing your counter by 1. So this always block gets sensitized for every positive edge of clock, and you are counting, count I becomes count I plus 1. So that is what this logic means. This infers a perfect 4-bit counter. So this is the sequential block of your design. And then comes this last statement, assign count equal to count I. So this is a plain assignment. This always the assign statements infers only combinatorial circuits. So here you first have an always statement with the positive edge of clock, which infers a sequential logic, and the assign block which assigns count equal to count I, which infers a combinatorial block. So this is actually in line with our generic view of our flip-flop, of our design. Design is having a combinatorial logic, a combinatorial cloud, and in between sequential elements. So what do we have now? We have the counter done. Now let us go to the comparator. So comparator has this is the design of the comparator. It has again a 4-input comparator, comp I, then there is an output comp O, and comp O is 1. This is a particular, it's a very good Verilog statement. So assign comp O equal to 1 when comp I is 0, and when it is not 0, assign 0. So this will look at the input and always create a 1 whenever your input comp I is 0. So that is the comparator we have designed. And now what are we doing? We are actually putting chip top with those two modules we designed, counter and comparator. So you can observe one important thing. The comparator is designed using some high-level constructs like assign. The counter is designed using always statements and a couple of high-level constructs to infer your design. But in chiptop.v, you don't see any of those always statements or assign blocks and all. Here, only modules are instantiated. This type of coding is called structural coding. Whereas when you design using, or when your Verilog code contains high-level statements like always, assign statements, and which infers basically sequential and combinatorial circuit using high-level language constructs, it is called behavioral coding. Structural coding, you don't put high-level constructs, you simply stitch just like a schematic module. So chiptop.v here is designed using only structural constructs. So, it is very important because I mentioned in previous session about netlist, finally after synthesis you get netlist and all. So netlist and all are designed using structural design constructs rather than behavioral design, behavioral coding. So it is important that both you learn both behavioral and the structural design techniques.